Hello guys, welcome back to my channel. In today's video, we will tackle another problem related to determining the maximum soil bearing pressure at the base of the footing. So let's dive into the problem. The concrete footing shown below is subjected to a loads from a pre-engineered steel building columns. Assume the footing is rigid compared to the soil. The density of the soil is 110 pounds per cubic foot, or PCF, and the density of concrete is 150 pounds per cubic foot. We are required to determine the maximum bearing pressure under the footing. And as you can see here in the figure below, we have the profile of the foundation or footings. We have the vertical loads due to the concrete and due to the steel columns from the pre-engineered steel building. And we have the horizontal reaction loads, 11 kips. The pedestal size of the pedestal is 16 inches by 16 inches. And it is a 4 feet deep from the top of the soil to the top of the footing. And we have the depth of the footing 1.5 feet, and it is an isolated footing 9 feet by 9 feet. So let's dive into the solution for this one. First of all, we need to determine the overturning moment because we have the lateral loads. So the overturning moment is simply 11 kips times 5.5, which is equal to 60.5 kips feet. So we have the lateral loads here. So the tendency of the footing, it will tend to rotate in a counterclockwise direction. So we will take this as a 2. It will rotate at this point. So this is our reference point for all the overturning moment. Then the next one is to determine the resisting load. So all the vertical forces, vertical loads, we consider it as a resisting load. Example for soil, we have the overburden soil and the pedestal and the weight of the footings. So those are the resisting load. So here, vertical loads, we have 70 kips, and the footing weight, we have 9 feet times 9 feet times 1.5 depth times a density of 150 pounds per cubic foot is equal to 11,225 pounds, which is equal to 18.23 kips. So the pedestal is 16 inches by 16 inches. We'll divide it by 144 to convert it into feet to be consistent with our unit. Then we will multiply it by 4 feet, which is the height of the pedestal. Then times 150, the density of concrete, and it will give us 1,066.7 pounds or 1.07 kips. So that is the contribution weight of the pedestal. Now the overburden soil, we have the 9.9 feet by 9 feet. We will deduct the area of the pedestal because we have already accounted that previously in here. So times the height, 4 feet, times the 110 pounds per cubic foot, it's equal to 34,896.4 pounds or equal to 34.9 kips. So the total vertical load, the resisting load is equal, R is equal to 70, which is the vertical load from the columns. Then the 18.23, the footing weight, and 1.07, the weight of the pedestal, and also the 34.9, that is the overburden weight of soil, which is equal to 124.2 kips. The next one is to determine the resisting moment. So the RM is directly the total vertical load times the 9 feet, which is the width of the footing, divide by 2. Because all this overburdened soil, the weight of the pedestal, the footings is aligned with the center line of the column. So they have only one moment arm, which is 9 divided by 2. So the next one is to determine the location of the resultant force. We have already determined the resisting moment, the vertical loads. Then the next one is to determine the location of our resultant. So the formula or the equation to determine the location load is the Rm minus the overturning over the total resisting load, which is 508.9 kips feet, which is this one, minus the overturning moment, which is this one here, and divide by the total resistance load, 124.2 kips, which is coming from here. So we have the location of 4.01 feet. That is the location of our resultant load, reference from the 2 going in the right side. So now, if you can see here in the profile, we have the resultant load and the location of our x from the 2 from the sides. So if we calculate the eccentricity, so eccentricity is just simply L over 2 minus x. So L, this is L over 2 minus x, that is our eccentricity, which is 9 feet over 2 minus 4.01, which is the x bar, equal to 0.44 feet. This is our eccentricity value, 0.44 from the center of the footing. And we have the condition here, if our eccentricity is less than or equal to L over 6, which is our kern limit. So this one we are okay, meaning the base of the foundations are effective. And if it is greater than L over 6, which means there is tension in our soil bearing pressure. So we will continue to check whether it is within the limit of kern. And L over 6 is equal to 9 divided by 6, that is 1.5 feet, which is greater than the value of E. So meaning the entire base of the footing will be effective and no tensions occur. So if that would be the case, the profile of our pressure at the base of footing is trapezoidal shape. So we have the minimum here and we have the maximum in here. So to determine the soil bearing pressure, the equation is R over BL, which is the width of the footing times length, all over 1 plus or minus 6 times the eccentricity divided by L. So that is our equation. That is valid only for rectangular shape of footing. So the minimum pressure based on this equation is 124, which is our R, then divide by 9 times 9, the dimension of the footing, which is BL, times 1 minus 6 times the eccentricity, 0.49 over L. So the minimum soil bearing pressure at the base of the footing is 1.03 ksf, kips per square foot. Now the maximum soil bearing pressure, which is here, we have 124.2 kips divided by 9 times 9 feet times, close parenthesis, 1 plus, because this is maximum, 6 times 0.49 feet over 9. And that would give us 2.03 ksf. So that is our final maximum soil bearing pressure. So that's all, guys, and thank you for watching. And if you find this video helpful, please don't forget to like and subscribe. All right. See you next time. Take care. Bye bye.